Welcome to this explainer on master trip logic. Today, we're diving straight into the central switchboard of power system protection. We are looking at the absolute critical junction that takes a localized fault detection and turns it into a perfectly coordinated, plant-wide shutdown. So what actually happens after a relay detects a fault? Well, think about it like this. Every protection function we've covered so far, differential, overcurrent, thermal, is essentially just a witness. They watch the system, and when something goes wrong, they raise their hand. But the master trip logic, that is the judge. It's the single point where every single protection stage's verdict converges to actually execute the final decision. Because honestly, if you get this wrong, even the most perfect sensitive fault detection in the world means absolutely nothing. In the system we're analyzing, this mastermind function is known as TRPP-TRC. Its whole job is to take a fault detected by a relay, like TR2PDF, for example, and execute the response. See, a fault at a major asset like a generator transformer block requires taking multiple immediate actions simultaneously. You can't just trip one breaker and call it a day. The master trip logic ensures that a perfect fault detection isn't rendered completely useless by a fragmented or partial failure to act. Here is how we'll map out this journey today. We'll cover the master trip function, coordinated multi-breaker tripping, the need for speed, high-speed outputs, and finally wrap up with incident energy and safety. Let's get right into it. Section 1, the master trip function, also known as the central switchboard. You can think of master trip logic exactly like a building's fire alarm control panel. No matter which smoke detector triggers first, the panel's job is to sound every single alarm and unlock every exit door at the exact same time. If the panel itself is slow, or if it only unlocks half the doors, having the fastest, most sensitive smoke detector in the world doesn't help anyone, right? The central brain must be flawlessly coordinated. To actually pull this off, the TRP-TRC function takes inputs from literally every protection element out there. Differential, restricted earth faults, thermal, mechanical, overcurrent, you name it. It processes those inputs and issues coordinated trip outputs to all the necessary breakers and systems. For a generator transformer block, that typically means simultaneously opening the generator breaker, the grid breaker, and initiating field de-excitation. Every single thing that feeds the fault must be shut down at once. Moving on to Section 2, coordinated multi-breaker tripping and the danger of the coordination gap. Now, I want you to really think about this from a protection engineer's point of view. If your differential protection detects a fault in absolute record time, but your master trip logic only sends a trip signal to the grid breaker and completely forgets the generator breaker, have you actually cleared the fault? Is this system truly safe? The answer is a definitive no, because the generator is just going to keep right on spinning and feeding current into that fault independently. This is exactly why testing the master trip logic to ensure all systems actually receive and act on the command is absolutely vital. A coordination gap here completely undermines every single protection function upstream of it. It seriously doesn't matter how meticulously you tuned your differential relays. If the trip output misses a breaker, the fault persists. Which brings us to Section 3, the need for speed, racing the clock. 4 to 6 milliseconds. In our day-to-day lives, that's literally imperceptible. But in power system protection, it's a total game changer. 4 to 6 milliseconds is the exact amount of time you can save on trip signal propagation just by upgrading your physical output hardware. Section 4, high-speed outputs, specifically looking at the BIO0007 module. Standard relay power outputs usually rely on electromechanical or standard solid-state stages, and, well, they have an inherent physical operating delay. That delay adds directly to your total fault exposure time. However, by utilizing the optional BO007 module's high-speed outputs, the master trip logic drastically reduces the time it takes to physically send the signal to open the breaker. It completely bypasses that standard delay, saving a precious 4 to 6 milliseconds. Section 5, incident energy and safety. Because in this industry, milliseconds equals skin and tissue. Look at how incredibly fast heat accumulates during an arc flash. Within just 0.15 seconds, that is 150 milliseconds, copper is literally vaporizing and catching fire. By 0.2 seconds, steel is burning. The conversation here isn't abstract electrical theory anymore. It is about explosive, highly destructive heat. The math behind all this destruction comes right back to the I squared T relationship we've talked about before. Damage energy is proportional to the square of the current multiplied by time. Because the fault current is squared, that tiny 4 to 6 millisecond savings we get from high-speed outputs disproportionately reduces the thermal and mechanical stress unleashed on the equipment. If you've got a massive fault current, shaving off even a few milliseconds removes a massive chunk of the total destructive energy. So, what you really need to take away from this is that reducing clearing time isn't just some fun engineering flex. It physically lowers the incident energy, which is measured in calories per square centimeter against human skin. In a practical, day-to-day scenario for maintenance workers, that reduction can be exactly enough to shift a task into a lower personal protective equipment category. This significantly improves both safety and worker mobility, which is a big theme we'll return to when we discuss arc flash mitigation later on. So I'll leave you with this final thought from the perspective of a safety engineer. If you verify a 4 to 6 millisecond clearing time improvement and it puts your incident energy just below a major PPE boundary line, is it worth rerunning the arc flash study? The answer is a resounding yes. A safety-conscious engineer absolutely must rerun that study because those meticulously engineered saved milliseconds might just change the safety protocols for everyone on the floor and ultimately save a life. With detection and coordinated tripping now covered for the generator transformer block, we'll shift our focus over to protecting the stationary power transformer in Section 4. See you there.